I hope all of you are able to see my lecture slide.
Sir.
Yes, sir.
Okay. I guess I started recording. Okay. Okay. So let me start today's lecture. Okay. So when it, I think what basically we are talking about, okay, we talked about thermally activated plastic deformation of metallic materials. So typically, okay, there are various multiple mechanisms will be happening during plastic deformation of materials. When you talk about, okay, as a function of temperature, when you take the material to different temperatures, okay, the rate controlling mechanism is going to change. Okay, the type of rate controlling mechanism, what it is going to change depends on crystal structure. Okay, depending on crystal structure and temperature, depending on temperature, the type of rate controlling mechanism is going to change. So the rate controlling mechanism will be, okay, will be known, okay, depending on, okay, the kind of multiple mechanisms what you are talking about. If they are, okay, if they are, okay, sequential, we do see slowest one is the rate controlling mechanism. If we do see processes which are independent process, there actually fastest one is the rate controlling mechanism. So in case of, okay, if I take a simple example of aluminum, okay, yet as a function of temperature, at low temperatures we do see intersection of dislocations, okay, which are basically all these are thermal barriers. Okay, intersection of dislocations going to control, okay, the deformation mechanism in aluminum, okay, at low temperatures. Once you go to higher and higher temperatures, we do see, okay, being a high stacking fault energy, metal, so cross slip is going to get activated very easily. Okay, so cross slip is going to be a, okay, rate control mechanism between this temperature 0.25 to zero point 0.5 times of melting point. Once you go to high temperature above 0.5 times of melting point, we do see climb is the rate control mechanism. So most of the cases, look at here, when you talk about deformation happening, plastic deformation taking place, means, okay, if there is a dislocation activity, climb is the rate control mechanism, okay, at high temperatures. Okay, so then we also had discussion how to determine, okay, activation volume, because we know that activation volume is defined as, okay, change in activation energy or enthalpy with stress. Okay, that is called activation volume. So the activation volume, okay, is basically can be determined from different tests by using tensile testing or creep testing. One can actually determine activation volume in, okay, materials as, okay, when it deform at different temperatures, okay, conditions, will come to know what kind of, okay, rate controlling mechanism is taking place. Typically people do jump test because we want to know within a okay, given a strain, okay, what is the, okay, at a particular strain, what is the change in, okay, temperature can lead to change in stress. One can get actually, okay, this kind of, okay, using these equations we can determine the activation volume. So activation volume is basically indicates that, okay, the volume of, okay, material, okay, the dislocation volume which is being, okay, controlled by the thermal barrier, by the thermal barrier. So when I say thermal barrier, barrier has a particular size d star, okay, d star, and dislocation has a length l star that is being controlled by the d star of a, okay, d star, the size of the barrier. So when you multiply Burgers vector and l star and d star, that basically gives activation volume, okay, which is basically controlling the plastic deformation of a material. Okay, so I think we had this discussion. Then I think we started having discussion about creep deformation. Okay. We have started having discussion about creep deformation, which is a high temperature deformation. Okay, one of the high temperature deformation phenomenon. Okay, so creep can also happen at low temperatures, but okay, so I think somebody's mic is on. Seems okay. So I think I don't know whose mic is on. Okay, just can you? Okay, and now it's better. Okay, So we started having discussion about creep deformation. Okay, so what we are talking about, high temperature creep deformation. We do see deformation. Okay, creep can happen even at low temperatures also, but the amount is negligible. Okay, the strain what we see due to creep is very negligible. So we have defined basically creep is a time dependent plastic deformation, okay, which can happen under constant load or stress at elevated temperatures. Okay, that's what called creep, okay, deformation. Okay, so there are different, okay, examples where actually creep is the important phenomenon. Okay, we have seen glaciers. Okay, glaciers are going to get, okay, go undergo deformation with, okay, time. So ice, basically ice is undergoing a creep deformation. That's one example. And we also had example of a, okay, incandescent bulb filament, tungsten filament. Because of its weight and high temperature, we do see there is a slowly creep deformation take place. After some amount of time, okay, we are going to see that filament is get fused out, okay, because of a creep deformation that can happen in the, okay, filament. So the third example, okay, basically I think most important, okay, engineering point of view, most important actually is a, okay, gas turbine. Okay, turbine. If you see gas turbines, we have a some kind of blades, turbine blades. So these turbine blades, okay, is used, okay, for in the gas turbines. What we are talking about, it's simply called jet. Okay, can be used for jet engines. Okay, can also be used for power generation. So these turbine blades undergo significant amount of plastic, creep deformation. Okay, significant amount of creep deformation. So one has to understand the creep deformation behavior of, okay, this gas turbine, okay, blades, the material which are being used for gas turbine blades. One has to understand creep deformation of a material. Okay, so if I see small video which basically shows, okay, how the, okay, jet engine works. Okay,
The turbofan engine is a complex synchronization of several components working together as two parts. A core section that produces power to drive the propulsor section that produces thrust. Thrust is a force created by the acceleration of air. This phenomenon is simply an application of Newton's second law of motion, commonly expressed as force equals mass times acceleration. It is this force that propels the aircraft. To see how this thrust is developed, let's look at the internal workings of Pratt & Whitney's PW4102 turbofan engine. The first component in the engine is the huge 9-foot diameter fan that rotates 2,800 times a minute at takeoff. This giant fan sucks in enough air to vacuum out the air in a 4-bedroom house in less than half a second. As the air races through the massive fan, it's separated into two streams. Only 15% of the air flows into the interior core of the engine. The remaining 85% of the air is ducted along the outside of the core and is forced through an ever-narrowing space, the fan duct, picking up speed along the way. The ratio of this air bypassing the core to the air passing through the core is called the bypass ratio. Because of its huge volume, the bypassed air only needs to accelerate a small amount in order to develop an enormous amount of thrust. Meanwhile, the other 15% of the air has entered the first component in the engine's core, the low-pressure compressor. Here, the air passes through several smaller stages, each consisting of a set of rotating blades in between a set of stationary blades. Each stage compresses the air, forcing its temperature and pressure to rise. After passing through the low-pressure compressor, the air enters the high-pressure compressor, which rotates faster and is responsible for 70% of the total pressure rise. After the air has passed through both compressors, it is 35 times higher in pressure and 1,000 degrees hotter than the outside air. The compressed air is now at the right pressure, but it is moving too fast to be efficiently ignited. So it enters a diffuser, where it slows down while remaining at the optimum temperature and pressure. The air then enters the combustor, where its energy level is greatly increased. This is accomplished by adding fuel through a series of injectors and igniting it. further increasing the temperature of the mixture by 1600 degrees. The higher the pressure of the air, the more energy will be added during combustion, and the more efficient this process becomes. This is why the compressors were used to increase the air's pressure. Now, the superheated and compressed air mixture is ready for the next phase. Blasting through the high-pressure turbine, the high-energy air spins the blades at over 10,000 revolutions per minute. These blades are connected to a shaft that runs through the center of the engine and drives the high-pressure compressor. In fact, the only purpose of the high-pressure turbine is to extract enough energy from the air to turn the high-pressure compressor. Together, these components make up the high spool. Next, the air passes through the larger low-pressure turbine. This turbine has two purposes. First, it extracts enough energy from the air to power the low-pressure compressor at the front of the engine core. These two components are connected via a second shaft, which actually passes through the center of the high spool. However, the second and more important job of the low-pressure turbine is to turn the large titanium fan blades up front. The fan is connected to the same shaft as the low-pressure compressor and low-pressure turbine. Together, these three components make up the low spool. Finally, the combusted air races out through the exhaust nozzle at the back of the engine to be accelerated one last time. The speed at which this gas exits the nozzle is called jet velocity. This exhaust stream produces only 20% of the engine's total thrust. The remaining 80% is produced by the large volume of accelerated bypass air exiting the fan duct.
So, hello, am I there now?
Sir, you are
Hello.
audible.
Yes, sir. Yes, sir.
Yes, sir. Okay. So basically, this is a nice video which basically shows demonstrates how a gas turbine engine works. Okay. So the gas turbine engine has a several components. Several components. Most of these components are exposed to high temperature, but the temperature range is going to change from one location to other location. So usually we need to have a higher the temperature. Okay, we do expect a higher efficiency of the process, so that can lead to better functionality of the overall gas turbine engine. So can anybody say what is the temperature rise we can see in this during this burning combustion? What is the temperature rise? What is
1500 to 1800 degrees.
yeah, higher the temperature is always better. Okay, in this video it says 1600 degrees Celsius. Okay, so we always intend to go for a higher and higher temperature for better efficiency reasons. Okay, I think all of us know about the thermodynamically higher the temperature, we can actually expect higher the efficiency of the process. So, but when you say you're talking about high temperatures, 1500 to 1800 degrees Celsius, at high temperature zone. Okay, low temperature is a low temperature zone also, where actually temperature will be less than 1000 degrees Celsius. Okay. So, but we do use this whatever is talking components are made of what? What are is made of what? Can anybody say the components which are present in this gas turbine? Made of what type of materials?
Sir, nickel alloy.
Nickel supplies.
But what is the melting?
Titanium.
Yeah, what is the melting? What is the melting point of nickel and titanium? Any idea? What is the melting point of nickel and titanium?
Nickel sweeper alloy will go till 2000, more than 2500, I guess.
No. The melting point itself is a 1470 degrees Celsius. Okay, just look at just see what is melting point of titanium and nickel. Both of them almost close by. Okay, around 1500 degrees Celsius, maximum 1500.
Titanium is 1668, sir, degrees centigrade.
Yeah, nickel. Okay, nickel is 1473 or 70 some 76. Okay, so the temperature is actually still below. Okay, because we are talking about 1600, 1800, but melting point is actually below the temperatures. Okay, but we do use those materials in this gas turbine, okay, engines. How these materials are going to survive at those temperatures? Any idea? No? I think somebody from
Coating, sir?
DMR or DRDO should tell. Okay, so there are coatings. Okay, you're right. Okay, so people use some thermal barrier coatings. Okay, TBCs. Okay, so on a metallic component, there will be some coatings will be given, and also airflow will be there. Okay, below the in the component, below the metal component, there will be some airflow that basically lowers the temperature. Okay, acting on the metallic component. So typically, the temperatures can be anywhere between 600 to 900 degrees Celsius. The metal component is going to experience temperature 600 to 900 degrees Celsius. Okay, but if we go to, for example, 2000 degrees Celsius, if I want to have a 2000 degrees Celsius, the metal component should bear temperature greater than 1200 degrees Celsius. Okay, around we need around 1200 degrees Celsius need requirement. So people are trying to explore better way of increasing the thermal efficiency of the jet engines. So one of them basically thermal barrier coatings that can actually facilitate increased temperature on the component, but below that coating, the metal what is going to experience the temperature is going to be around between 600 to 900 degrees Celsius. Okay, so the temperature, if I say take for example 900 degrees Celsius, okay, it is about 0.5 times of melting point of a titanium or nickel. Okay, below, okay, there is not above 0.5, it's above 0.5 degrees Celsius. Okay, it comes around 0.7 or something. Okay, so what you are talking about, okay, even the temperature how outside ambient temperature there, it's a high temperature, but metal component is going to experience low temperature relatively. But even then, okay, that temperature itself is 900 is a quite high for a metal component. So that's where we are talking about creep deformation. The metallic components will experience significant amount of temperature. So there actually, okay, we do see the material is undergoing some kind of creep deformation. Okay, so is it clear about the importance of creep deformation studies? Okay, so if I look at here, okay, turbine blade. Just if you take one component of turbine blade. Okay, in the jet engines, turbine blades actually major volume of the thing is constituted by turbine blades. So turbine blades can be of a polycrystalline or directionally solidified, can also be a single crystal. Okay, so equiax crystalline polycrystalline structures are relatively cheaper as compared to DS grade, whereas single crystals are actually relatively expensive in nature. So if we use single crystals as a turbine blades, single crystal material, okay, we talk about nickel based superalloys which can be produced in all these forms. We can produce polycrystalline, okay, we can produce DS grade, single crystal also can be produced. Okay, but the cost of whole thing is going to be, because the way we produce single crystals is a costly affair, okay, whole thing. So that leads to overall thing is expensive. But in terms of creep resistance, okay, single crystals perform outstandingly as compared to DS grade. DS grades perform better than polycrystalline materials. Okay, so the fan blades, the people are taking different types of designs. Okay, if you talk about low temperature fan blades, okay, which basically initially used to have a narrow cord kind of thing. Now we have a wide cord, okay, less number of blades, okay, and wide cord kind of design. Okay, these are design aspects. Okay, so these are titanium based alloys, okay, used. Okay, and also people try to have a honeycomb kind of structures, so that you can reduce the still weight of the component. Okay, so but as far as high temperature turbine blades are concerned, nickel based superalloys are quite commonly used. So that structure can vary from equiax polycrystalline to DS grade to single crystal. So if you can use single crystals, okay, those blades perform much better, okay, than any of these other two structures. Okay, so we understand why single crystals perform better than DS grade, and DS grade better than polycrystalline structured nickel based superalloys. Okay, so when you talk about superalloys, okay, typically, okay, if I take a particular, okay, material, say polycrystalline, so superalloy, okay, superalloys can be, I said, okay, it can be different, microstructure can be different types of microstructures. So within a superalloy, okay, we do see the microstructure of superalloy typically contains, okay, gamma prime precipitates, within a gamma matrix. Within a gamma matrix. Gamma matrix is basically nickel matrix, nickel based superalloys, and gamma prime is basically Ni3Al, nickel aluminide. Okay, Ni3Al is an intermetallic compound, okay, which is a gamma prime precipitates. So if you look at here, the superalloy, okay, contains more than 50% of precipitates, gamma prime precipitates. Gamma prime precipitates will be more than 50%. Okay, and apart from, okay, gamma prime, we also see, okay, some other, okay, kind of compounds like a metal carbides. We do see metal carbides, and we also see, okay, some kind of, okay, carbides or borides around the boundary, okay, around the boundary of a grain boundary of a material. Okay, so look at here. I think what you're talking about, we are talking about gamma prime and carbides, borides, so many things. Okay, we do see intragranular, intergranular, so different types of, okay, compounds are present. Okay, the strengthening and the creep resistance is getting derived, okay, by having different types of precipitates and, okay, carbides and borides. Okay, so if, why do you say it's a super alloy? Okay, can anybody say why do you say super alloy? Because we said nickel based superalloys. Okay, okay. Why do you say superalloys? What was the reason for actually giving that superalloy terminology? Any idea?
I mean, this yield point anomaly is one of the reason. The strength yield point anomaly, that
Which one?
strength,
What is that?
increases with temperature, and also we can use it at higher temperature. And again, as you said, creep properties are definitely better here.
Mm-hmm. Okay, so usually, okay, superalloys, okay, usually, okay, because of this gamma prime precipitate presence can lead to, okay, instead of decreasing stress with increasing temperature, usually strength increases, okay, up to certain temperature. Okay, up to certain temperature around 800, 900, depending on, okay, what type of this gamma prime. Again, gamma prime can also be alloy precipitate, can also be a alloyed precipitate. So we do see, okay, strength typically increases, okay, with increasing temperature up to 800, 900 degrees Celsius. Afterwards, again, decreases with increasing temperature. Okay, so that is a called anomaly. Okay, that's a okay, plastic deformation anomaly. What we see in superalloys. Okay, the term superalloys come because this alloy, okay, superalloys contain, okay, at least 10 alloying elements, at least 10 alloying elements. Each alloying element has its own functionality and a reason. There is a purpose for adding each alloying element. Okay, that's why it's called super alloy. Okay, if you see the type of, okay, alloying elements, what we see, okay, here various alloying elements are being used. Okay, in a nickel, if we take a nickel matrix, okay, we do see various type of alloying elements are present. Some of the alloying elements, okay, can go into a gamma matrix, strengthen the gamma matrix, solution strengthening can take place. Some of the alloying elements can go to a gamma prime intermetallic, can go to intermetallic. Some alloying elements can form, okay, carbides or borides. Okay, like for example, boron carbon element present can lead to formation of, okay, between the some, okay, high tendency alloying elements. Okay, like titanium can form titanium carbide. Okay, if you talk about boron, okay, tungsten boride, okay, chromium borides can form. Okay, so different types of carbides and borides can form, okay, along the boundaries, which basically controls the, okay, migration of the boundaries. Okay, we do see stability, thermal stability of the structure is going to be improved by having, okay, certain, okay, precipitates along the, okay, boundaries. Okay, that's why actually we do say these alloys which contain, okay, at least 10 alloying elements and which exhibit increased or almost steady strength with increasing temperature are called superalloys.
Sir,
Okay. Yes.
sir, as you say, there are in general more than 10 elements. So can we
Yes.
not say these superalloy high entropy alloys also?
No. No. High entropy alloys actually has a particular ratio. You need to maintain particular ratio. Okay. This cannot be cannot come under high entropy alloys
Okay, sir.
because we know that there is a definition. Configuration entropy. We need to have a particular entropy. Then only call high entropy alloys. So if you calculate, and these alloys will not come under. Super alloys will not come under high entropy alloys. Any more doubts? Okay. So this is actually kind of importance of what we were talking about creep. So as far as engineering application point of view, okay, turbine blades, discs, which are made of high temperature alloys. Okay. So one of them actually nickel based alloys of cobalt. And super alloys can be of different types. Nickel based, cobalt based, or iron nickel based super alloys. Broad classification of super alloys. Depending on the matrix. The matrix can be of rich in nickel or actually matrix rich in iron plus nickel. It can also be matrix rich in a cobalt. Accordingly, we say cobalt based superalloys, nickel based superalloys, iron nickel based superalloys. So there are various, I think n number of superalloys have been developed with an intention to have a better and better creep resistance and thermal fatigue resistance. So now let's talk about what is creep deformation. The creep deformation, typically, if you want to understand creep behavior of a material at a laboratory scale, what should you do? Because the definition itself says we need to induce some plastic deformation. Okay, the plastic deformation has to be induced under constant load or stress at elevated temperatures. So what here we have to take a tensile specimen like a dog bone shape and subject it to constant load or stress and heat the material, the specimen, to certain temperature. Okay, fix the temperature, fix the load or stress. Okay, then what happens with at the temperature and stress? We may see the specimen is going to get elongated, gets elongated. Okay, with time, with time. If I monitor if I monitor the displacement or extension in the specimen as a function of time, as a function of time, so that basically gives me a raw data, displacement or extension as a function of time. Okay, now already know what is my gauge length. I know what is the gauge length I'm using. Okay, if I divide with the gauge length, I get a strain. Am I right? So strain versus time. If I make a plot, strain versus a time, a typical we get a typical creep curve like this. We do get a typical creep curve like this. Okay, typically. Okay, so the moment when you apply load, at temperature already heated the material specimen to certain temperature, when you apply load, we do see there is a sudden deformation, some amount of deformation, will take place. It can be elastic or some amount of plastic deformation also can take place. Okay, depending on magnitude of stress, we may see some instantaneous strain. It is called instantaneous strain. It can have a elastic plus plastic strain depending on how much stress you are applying. Okay, after certain amount of time, with the time, we do see like this. Okay, the strain can be like this, then becomes almost like a linear kind of thing, then again increases here. Okay, so a typical creep curve will have three stages. One, primary creep, then secondary creep, then we'll have a tertiary creep. Tertiary creep. Okay, the slope of this curve at any between any 2 points basically gives you strain rate, gives you strain rate. Okay, if I take the slope in the linear portion, here the linear portion, that strain rate is called creep rate. That strain rate is called creep rate or steady state strain rate, or it's also called minimum creep rate. Minimum creep rate. Okay. So when you talk about three stages, now if I take a slope of slope of this curve in this primary stage, what's happening with increasing time? What's happening to the strain rate? Is it increasing or decreasing? just between, okay, from here to here,
Decreasing.
it decreases, okay, it decreases, okay. Here it's almost constant, okay, it decreases, initially it's decreasing, then becomes a steady, then again, okay, in the tertiary stage we are seeing again increasing strain rate, okay, increasing strain rate. So this typical curve, whatever okay, we are talking about, this shape is going to vary depending on, okay, magnitude of temperature and stress. Depending on magnitude of temperature and stress, higher the temperature, okay, for example, with increasing temperature or with increasing stress, typically, okay, the shape is going to change, okay, like this. Same material, if I deform material, okay, either at low, once fix the temperature, if at low stress, high stress, medium stress and high stress, okay, I do see the rate of, okay, if you look at the amount of strain or strain, okay, what you are seeing is going to increase at a given time with increasing stress. Similarly, with increasing temperature also we do see increasing, okay, strain or, okay, deformation in the material is going to increase either increasing temperature or with increasing stress, okay. So accordingly, okay, we may see the short, the life, okay, the overall period of a primary creep, okay, primary creep or secondary creep can going to get shortened, okay, with increasing temperature or stress, okay. So I said actually if you take this particular, okay, stress tank curve, this particular creep curve, okay, the creep curve is obtained, okay, under constant stress, under constant stress. Okay, under constant stress, how this creep curve is going to be typically like this. If you convert, okay, this thing into a strain rate, okay, the strain rate is going to decrease, then becomes a steady, then again it's going to increase, okay. That's why we take, okay, this is a called steady state creep rate or minimum creep rate, because the strain rate, the rate of deformation, okay, in terms of the rate of displacement in the material, okay, with the time is basically it's almost minimum, okay. That's is called minimum creep rate or steady state creep rate, okay. So this is actually for, okay, fundamental understanding, scientific understanding purpose, we need to know, okay, this steady state creep rate, okay. Steady state creep rate has to be known, okay. Then we can know, okay, how long the particular material is going to survive under a given set of temperature and stress conditions, okay. So if I look at here, I said we can deform material under constant load or a constant stress. Okay. But for scientific understanding, for fundamental understanding reasons, one has to deform material at a constant stress. At a constant stress. However, experimentally, okay, there are difficulties. Okay, if you want to, we have to maintain a constant stress is not easy stuff. Okay, we have to give a some closed loop. So equipment wise, okay, it's going to be costly. Okay, overall equipments if you want to maintain a constant stress. So most of the times, what people do, they do generate curve at a constant load, okay, rather than under constant stress. But it's better to, okay, do at a constant stress if possible. If the instrument, if you can have an instrument which can maintain constant stress. So, for example, same material, if it was deformed, one under constant load, other one under constant stress. Okay, look at here, we do see differences. Okay, depending on whether you're maintaining constant load or a constant stress, accordingly, we do see, okay, the amount of strain that is taking place for a given time is going to change. Okay, after, okay, in under case of constant stress, it may go to tertiary creep, but after some, okay, long time, okay, this also undergo, but actually what we are seeing an extended steady state creep in case of a constant stress for the same material, same temperature. But under constant load, we are seeing a, okay, early tertiary creep is getting initiated much earlier than under constant stress, okay. Can anybody say what was the reason for this thing? Why are you seeing such differences between constant load and constant stress for the creep curves?
I mean, the cross-section area of the sample will definitely reduce. So that's how constant stress means we are reducing the load to maintain the stress constant. While in constant load, definitely that is going to be more severe.
Yeah, your stress is basically locally is increasing. Okay, your stress is going to be increased because when the cross, because you're talking about tensile deformation here. Okay, the deformation, okay, in tension mode. So when you deform material, so that there is a cross section area going to decrease gradually when there is a strain in the material. Okay, So locally, what happens when the moment, okay, we under constant load conditions, you're maintaining constant load, but your stress, okay, your areas come down. So your stress is going to be higher, okay, under constant load. Okay, that's why actually we are seeing premature, okay, failure of the fracture of the specimen under constant load as compared to the constant stress. Okay, any doubts here? Are there any doubts?
Sir,
So in
yeah,
Yes.
go
One
ahead,
of
Alok.
yes.
So in actual condition, basically, constant load is the phenomena, right?
Um, yes, basically in the applications, constant load is okay, but understanding cannot get a proper, okay, understanding if you maintain constant load.
So we
But
should be so experimentally also does cannot we say कि constant load is the right experiment to do?
yes, only but that's why I said scientific understanding, okay, how stress is okay, affecting, okay, effect of stress. If I want to understand, it's okay. That's why actually constant load experiments are okay. Constant load experiments because in reality, okay, we may
And
see the component is going to subject to same load, okay.
yeah, and
So that
constant load is easier also, right, sir, to
it's much
perform.
easy, much
Yes.
easier, much easier. That's what I think. Okay.
Okay.
Because maintaining constant stress, always you have to monitor the change in, okay, strain, okay, change in, okay, displacement of the material, accordingly how to adjust, okay. Cross sectional area is going to change accordingly how to adjust the load. That means it requires a closed loop, okay. So someone else is asking. Let's go.
So I had the same question. So in real life, there will be a condition of constant load. So why are we concentrating on constant stress?
Yeah, so constant stress we have to understand, because for scientific understanding, okay, what is the effect of stress, okay, how the stress is basically influencing the behavior, okay, or material behavior. That was the reason, okay. What type of mechanism taking place. For example, I have to know what type of mechanism taking place. Typically, we never talk in terms of a load. We talk in terms of a stress, okay, strain kind of thing. Okay.
Yes,
So,
sir.
yeah. So this is a kind of, okay, when you talk about creep deformation. Okay. So this is where actually I said, okay, we need to have, okay, some kind of, okay, understanding scientifically what type of mechanism is taking place. If you know what type of mechanism is taking place, then I can tune the design the material, okay, so that I can control creep deformation of material. Okay. So if I can, okay, that's what actually where I have to know what is the effect of stress, okay, what is the effect of grain size, okay, in terms of we take a microstructure, grain size is important. What is the effect of temperature on a steady state creep rate? For a scientific analysis, we have to know what is the steady state creep rate the material is going to experience if we change the stress or grain size or a temperature. Okay. Okay, if we have a relationship, okay, which basically correlating the steady state creep rate with stress, grain size, and temperature, this is called constitutive relationship, constitutive equation. Okay, so this is the constitutive equation, well-known constitutive equation, okay, which has been established quite well for creep deformation of metallic or even ceramic materials also. So people have established, okay, this kind of equation. This equation is also called Dorn, DORN, Dorn equation. Who is the first one who has proposed, okay, the interrelationship between steady state strain rate, okay, and stress and temperature initially. Then people have added, okay, grain size and other things, okay. So this equation also called, okay, there's another thing people say, Bird Mukherjee Dawn equation. Bird Mukherjee Dawn equation. So basically initially Dawn proposed, after that I think some additions were taken into consideration, that finally the steady state creep rate can be expressed, okay, as a function of stress, grain size, and temperature. So here, okay, there are important, okay, A is a constant, D naught is actually, okay, diffusion coefficient, G is a shear modulus, B is a Burgers vector, K is, okay, Boltzmann constant, T is a temperature, sigma is a stress, true stress, okay, D is a grain size, T is a temperature, Q is, okay, here there are three important things, N, P, Q, okay, these are called, okay, constitutive parameters, constitutive parameters N, P, Q. Okay, so depending on deformation mechanism, okay, each deformation mechanism will have its own NPQ values. Will have its own NPQ values. Okay, so the n value can vary, okay, from 1 to 7. Typical, okay, creep deformation, okay, during creep deformation, high temperature deformation, the n value can vary from 1 to 7. The p value can be 0 to 3, 0 to 3, and the q, activation energy, can be a lattice diffusion or grain body diffusion or a pipe diffusion. Okay, can be a lattice diffusion. We already discussed lattice diffusion, boundary diffusion, and core or pipe diffusion. Okay, so depending on mechanism, okay, depending on this, okay, npq values, we have a particular type of mechanism. Okay, if I list down some important creep mechanisms, what we see at elevated temperature when you deform metal at, okay, at elevated temperatures. Okay, we do see, okay, low temperature climb, high temperature climb, creep. Okay, these are dislocation creep mechanisms, and we also see Navarro herring creep and Coble creep. Okay, this is actually, these two are common category of diffusion creep, and Harper Dawn creep. Harper Dawn creep. It is actually, okay, it happens under very low stresses and very high temperatures. Low stresses and very high temperatures, and we also see grain boundary sliding, which is a okay, kind of accommodating mechanism, which is going to happen during deformation of materials. Okay, so look at here the npq values. If I take, okay, if I take dislocation creep mechanisms where p is equal to 0, p is equal to 0. Okay, so that is basically independent of grain size. Dislocation creep mechanisms are independent of grain size. The n values are very high. Okay, 5 to 7. Okay, n equal to around, okay, n equal to, this is called, n is basically stress exponent. P is called inverse grain size exponent. Inverse grain size exponent. So the stress exponent can be, okay, n is equal to 5 or n also can be 7. Okay, look at here when I talk about depending on temperature, high temperature, low temperature, accordingly your diffusion, okay, the activation energy for diffusion is going to change. High temperature, we know that, okay, lattice diffusion is the, okay, rate controlling. Okay, whereas, okay, at low temperatures, when you talk about dislocations, you're talking about dislocation creep mechanism, dislocation play a role, so that core diffusion, okay, is going to take place. Okay, accordingly q value is going to change. In case of diffusion creeps are considered as a Newtonian, okay, flow. That material is going to undergo Newtonian flow. And I say Newtonian flow, okay, n is equal to 1. Okay, your strain rate, okay, directly proportional to stress. Directly proportional to stress. Okay, these are called Newtonian flow. Okay, when n is equal to 1. But this diffusion creeps have, okay, strong dependence on grain size, have a strong dependence on grain size. Okay, so when I talk about Nabarro herring, okay, we are talking about, okay, lattice diffusion. Whereas in Cobalt creep, when do you say Cobalt creep? When there is a grain boundary diffusion is the dominant one. That means a low temperature and high temperature phenomena. Low temperature and high temperature phenomena. Cobalt creep is a low temperature phenomenon as compared to Nabarro herring creep. So we also see Harper Dawn creep in certain materials, not every material. In aluminum, lead kind of materials, people have seen. Okay, it is neither, okay, diffusion creep nor a dislocation creep. If in terms of, okay, n value, it is a represent like a manifesting like a, okay, diffusion creep. Whereas in terms of p value, independent of grain size, it's manifesting like a dislocation creep. Okay. So this kind of the Harper Dawn creep is usually observed at a very high temperature, very low stresses, okay, in certain materials. So grain boundary sliding, this is quite commonly happens at high temperature. When you deform material at high temperatures, grain boundary sliding is going to take place, okay, as an accommodative mechanism. So what happens, okay, look at here, n value can be 3 or 2, can be 3 or 2. Accordingly your p value can be 1 and 2. Okay, and accordingly we see ql or qgb. Okay, depending on grain size. If the grain size is very fine, if the grain size is very fine, we do talk, okay, finer grain size where grain boundary fraction is more, we do talk, okay, the rate controlling diffusion is basically grain boundary diffusion. Okay, for the, okay, in the fine grains materials we have a n value 2 and p value 2. In a coarse grain materials, there also we do see grain boundary sliding where n is equal to 3, p is equal to 1, q is equal to ql. Okay, is it clear? Any doubts? Okay, so I think we do see, okay, a well-established equations. Okay, so for Nabarro herring, Koבל creep, Harper-Don, okay, low temperature climb, high temperature climb, okay, your n values, okay, are going to change. Okay, p values are going to change. Okay, so depending on, okay, what type of mechanism we are talking about. Okay, so when I deform a material at high temperature, at high temperature, okay, under stress, okay, typically what happens, there is a mass transport. We assume that is a grain, okay, grain of a size d. I'm deforming, okay, material under, okay, tension and other compression, for example. Okay, it is experiencing this biaxial kind of, okay, one tension, other one is compression. Typically what happens, there will be a mass transport, okay, under load. Okay, mass is going to transport towards the tensile direction. Vacancies are going to move towards compression side. So that can lead to, for example, initially this shape becomes a this kind of shape. That means there is a displacement deformation in the material. Okay, this is called creep deformation. Okay, so when I say high temperature means there we are talking about vacancies play significant role, because diffusion going to get be, okay, taken place. So that's why actually mass transport and vacancy transport, okay, can lead to shape change in the material. Okay, so depending on stress, okay, how much stress we are applying. If the stress is high, we do talk dislocation creep. If the stress is relatively low, we call, okay, we typically talk in terms of a diffusion creep. Because the stress dependency is low, that low stress we do talk diffusion creep at high temp, both of them high temperature. So accordingly we have a dislocation creep and diffusion creep. So when I say dislocation creep, okay, if we take a polycrystalline material in a grain, okay, if we take a grain, we may see at high temperatures we do see formation of some subgrains. Okay, subgrain cell structure, okay, can form during deformation. We may see formation of subgrains and cell structure that can, okay, so look at it depending on temperature. At low temperatures, okay, core diffusion going to dominate rate control mechanism, whereas at high temperatures lattice diffusion, okay, lattice diffusion is going to take place. Still we do see dislocation activity at high stresses. Once you go to, okay, so accordingly dislocation creep, you have low temperature climb and high temperature climb. In case of diffusion creep, okay, diffusion can take place, okay, through the lattice or along the boundary. Okay, if the diffusion takes place along the boundary, we take it, call it as a Koבל creep. If it happens through the lattice, okay, under deformation, under stress, we call Nabarro heavy creep. Okay, any doubts here? Are there any doubts? Am I there? Am I online?
Yes, sir.
Yes.
Yes, sir.
Okay, okay, fine. Yeah. Okay. So I
Sir,
hope
this
many of you might be. Yes, yes.
sir, this stress that we are applying, can we compare it with the yield stress, whether it will be less than yield stress or yield strength or
No,
greater?
we need to induce plastic deformation. Okay, we need to induce a plastic deformation. That's what I said. Creep is there. Okay, time dependent plastic deformation.
Oh, okay,
Okay,
sir.
so when you say yield stress, okay, yield stress, if we talk about at room temperature, okay, at room temperature, okay, if we talk about that's high stress. But once you go to high temperature, we have to talk, okay, we have to cross that yield stress at high temperature.
Okay, sir. Okay, sir.
Yield stress at high temperature. Okay, so that's, we should not get confused. Okay, if you talk about yield stress at room temperature, so that stress may be less than your yield stress room temperature, but that stress actually crosses above the yield stress of a metal at that temperature.
Okay, sir.
Yeah, that's why it's a time dependent plastic deformation. Okay, so if I look at here, okay, typically if I make a plot, okay, strain rate versus stress, strain rate versus,
Sir,
yes.
Sir, in practical situation, basically out of these given constitutive equation, how to decide? Because generally, I mean, there is no clear-cut margin. What is high temperature? What is high stress? So, on what basis I can choose which constitutive equation may be applicable to my data or my material?
Okay, see that's what look at here. Okay, this is where actually it basically talks about effect of temperature here. Okay, so we know that okay, creep deformation typically happens above 0.5 times of melting point. Okay, am I right? Why it's okay, the high temperature creep deformation? We do say there is a okay, homologous temperature is about 0.5. T by Tm is equal to 0.5. Okay, where at that temperature onwards diffusion, okay, is significant. Okay, the process of diffusion is a significant. Okay, below that temperature, okay, we do see negligible diffusion activity. Okay, so zero point 0.5 is the usually cutoff temperature. Okay, where we talk about high temperature, simply called creep. Below 0.5 times, people say logarithmic creep. Okay, logarithmic creep deformation, that's actually not so okay, significant. But when you talk about high temperatures above 0.5 times, so when I talk about above 0.5 times, okay, it can be 0.5, 0.6, or 0.9 up to melting point. Okay, it can be up to 1. Okay, melting point. So if you look at here, okay, this is for the high temperature around okay, zero point 0.9 times of melting point. Typical. Okay, this is about 0.6 or 0.5 times of melting point here. If you look at here, okay, at low temperatures, okay, we do talk okay, low temperature climb and high temperature climb. High temperature climb and low temperature climb. Okay. In case of a high temperature, we are talking about only one dislocation creep, which is nothing but n is equal to 5, which is a high temperature climb. We are talking only high temperature climb. At high temperatures, we do not see okay, low temperature climb. So we already discussed okay, in the previous lecture. I had shown okay, when I have grain boundary diffusion and okay, lattice diffusion here, grain boundary diffusion here. If I normalize with delta by d, it comes here. Then we'll come to know where the transition taking place. Am I right? If you remember in the previous lecture, I showed okay, lattice
Yes.
diffusion and Kramer. Okay, there is when I bring it normalize with delta by d, the dgb, I'll get okay. There is a crossover. We do see a crossover thing. Then we'll come to know okay, what is the transition temperature at which okay, we need to talk about lattice diffusion. At what temperature we talk about okay, grain boundary diffusion. Like that. Similarly, here also, when you talk about pipe diffusion, okay, pipe diffusion somewhere there, okay, and lattice diffusion somewhere here comes. If you normalize with some pre-exponent, some exponent, that also brings, that will basically gives a transition at which we are going to see low temperature climb and high temperature climb.
Got
Okay,
it.
so
Yes.
we have to establish that, okay, diffusion, okay, that equate both the things and see where the transition taking place. Okay. So the other thing, when I say dislocation creep and diffusion creep, okay, there is a transition for the stress, not for a temperature. Okay, dislocation creep happens at high stresses. Diffusion creep happens at low stresses. Okay, we'll come to know where the transition. How do you get a transition? Okay, in the next slide, we'll come to know where the transition for the in terms of a stress. Okay. So we know, okay, for example, within a dislocation creep, we have two low temperature climb and high temperature climb. So depending on temperature, okay, the way the transition taking place, okay, below that below the transition temperature, okay, that means low temperature, we do talk about low temperature climb. At high temperature, we talk about high temperature climb. Okay, there is a limit. Okay, above some stress, we do see breakdown, power law break. It's called power law breakdown. Okay, that means whatever talking about strain rate is proportional to sigma to power of n is typically power law. Okay, sigma strain rate is basically function of sigma to power of n is a power law. So beyond certain stress, we cannot use okay, we cannot use this equation. That is called power law breakdown. Okay, so at high stresses, at these stresses, we do not say it's a creep deformation. Okay, there's no power law break. So it's called exponential creep. It's basically simply called exponential creep regime. Okay, as far as applications are concerned, we mostly okay, consider the stresses below this exponential breakdown. Okay, below this power law breakdown thing. Okay, so here okay, the stresses will be typically the constant stress one you say, it basically comes below the stress. Okay. So look at here again, between now okay, we have a at high temperature, we are talking about okay, high temperature climb, and there's another thing okay, n is equal to 1 here, n is equal to 5. There is a transition here. So within this okay, within this okay, again below this, below the power law breakdown, again we have a two domains. Okay, at high temperature we do see okay, typically we do see n is equal to 1 means Newtonian flow, n is equal to 5 means a non-Newtonian kind of flow we are seeing. So this is a dislocation creep, and this is something related to diffusion creep, or can also be Harper-Down creep. Can also be a Harper-Down creep. Whether this Harper-Down creep is there or not, okay, how do you know? We have to see depending on grain size. Okay, if you go to effect of grain size, if I see here, okay, if I see effect of grain size, we know that, okay, effect of grain size is there for the diffusion creep. Finer the grain size, finer the grain size, higher the rate of rate of deformation. Higher the rate of deformation. That's why look at here at a given stress. Okay, coarse grain and fine grain. Okay, fine grain is experiencing more amount of strain. The rate of deformation, the strain in the material, okay, at for a given time is more in fine grain material than the coarse grain material. Whereas when you talk about within this dislocation creep domain, it's almost independent of grain size, because that's why actually your P is equal to 0 for a dislocation creep. Okay, so there's no effect of grain size in a dislocation creep. So the dependency, grain size dependence is 0 for a dislocation creep. Okay, is it clear? There's a lot of information in this slide. Okay, effect of grain size here. Okay, okay, effect of stress, effect of grain size on creep rate. Okay, here this plot basically relatively, okay, if we talk about only dislocation creep, we talk about only in this domain, if you're talking about, okay, the dislocation creep thing. So we do talk about, okay, low temperature climate, high temperature climate, relatively at, okay, high temperature, low temperatures, we do see low temperature climate is going to come into picture. Okay, so there's another thing. Okay, they also talk, okay, effect of stacking fault energy. Okay, this here there are two curves here. Okay, two different materials. Okay, stacking fault energies. Okay, this is a stacking fault energy of this particular material is greater than, okay, other material. Okay, if you take aluminum and copper, aluminum and copper, okay, aluminum has high stacking fault energy than the copper. Am I right? At a given stress, okay, at a given stress, okay, which is experiencing more strain at a given stress and given, okay, homologous temperature is fixed. Okay, T by Tm is equal to, okay, around 0.5, which is 0.6 whatever. Okay, at a given stress, okay, which material is experiencing more amount of strain for a given time? Low stacking fault or high stacking fault material?
Lost.
Huh? Just see here, okay, I'm talking about at a given stress and temperature. Okay, given stress and temperature and time, for a given time, okay, which material is going to experience, okay, between aluminum and copper, which is going to experience more amount of strain? I fixed, okay, homologous temperature is fixed. T by Tm is equal to 0.5 or 0.6,
Low
0.5,
stacking
okay,
material.
and stress. Low stacking fault, what's that?
Copper.
Copper is going to see more strain, creep strain. Here, see, look at here, okay, gamma 1 is basically gamma 1 is greater than gamma 2. Okay, this is the, okay, high stacking fault energy material curve. This is for the low stacking fault energy material. This is aluminum and this is the copper. Okay, now when I fix my stress, okay, which is experiencing more strain? Which is experiencing more strain?
High stacking fault energy.
High stacking fault energy material. Okay, high stacking materials will undergo easy cross slip, and climbing is also very easy. Okay, that's why actually we do see, okay, it's the same. Okay, what we see when room temperature also we talk about, okay, cross slip is easy, that's why actually recovery starts. Here also same thing, okay, high temperatures, okay, when you talk about high temperatures, high stacking fault materials will undergo for the same, okay, everything has been fixed in terms of homologous temperature stress. In that case, typically we do see, okay, high stacking materials undergo easy, okay, large amount of creep strain. Okay, so one has to control the stacking fault. If you can control the stacking fault energy, we can see an increased, okay, fatigue, creep performance, increased creep performance of the material. Okay, that's how people also do alloying. Okay, matrix can be strengthened with alloy that basically lowers the stacking fault energy. Indirectly, that also improves the creep resistance of the material. Okay, is it clear? Any doubts? Are there any doubts? Okay, so the next important thing, okay, is a deformation mechanism map. Okay, so it basically a map is a kind of a pictorial representation of okay various mechanisms which are happening as a function of some variables. Okay, as far as creep is concerned, the variables. What are the variables here? As far as okay, creep is concerned, the variables are stress
Grain size, temperature.
Wait.
and temperature. These three are variables. Okay, am I right? Okay, so stress, temperature, and grain size. So if I fix grain size, that means actually I can study effect of okay a temperature on stress. Okay, so or if I want to okay fix stress, I can know grain size versus temperature. Okay, so the deformation mechanism is nothing but pictorial representation of okay the domains of okay various mechanisms which can happen okay in a material when you deform material okay when you deform material as a function of these variables. Okay, Ashby was the first one who has introduced a map, okay, deformation mechanism map to represent, okay, various mechanisms which can happen in materials, okay. So a typical Ashby map, okay, usually constructed for a constant grain size. For a constant grain size, other two variables sigma and t. So these are normalized sigma by g shear modulus and t by tm, okay, melting point of the material. It's a normalized things, okay. So what he has done, okay, he has come up with a map to represent various mechanisms which can happen, and the domains of the maps, domains of the mechanisms have been identified by constructing a map sigma by g versus t by t. Okay, it became very popular. Okay, people use this left and right. Okay, so when you have design a material, okay, establish okay these things and see what kind of okay deformation mechanisms are taking place. Once you know this map, okay, I can say, okay, for example, I want to use the material, okay, at this temperature. I want to use a particular material, okay, for a component which can be exposed to a particular stress and temperature. That means the material is going to experience dislocation creep. That means the mechanism, what is going to be dislocation creep mechanism. So if you can control climb, if you can control the climb, that means you can extend the life of a component. Okay, because I already know my application, this is the temperature domain and this is my stress domain. Okay, this is my kind of okay in this domain, okay, what is the mechanism, climb mechanism. So if I can control climb, I can see, okay, I can extend the life of a component. So like that, okay, depending on okay stress and temperature combination, okay, I can see what type of mechanism is happening. Accordingly, I can actually take measures to control the particular mechanism in order to extend the life of a component. Okay, it became very popular. Okay, so any new material if somebody develops, they usually come up with this kind of maps, so that actually like an atlas of maps will be developed, okay, for a materials. So as a okay, once you change the grain size, accordingly the domains are going to change the size of the domain. It may okay, increase or shrink, okay, may expand or okay shrink, okay, take place depending on grain size. Okay, so very okay important way of representing graphical or pictorial representation of the domains of various mechanism maps as a function of okay variables, two of the variables at a another other one will maintain constant. So it's very used, okay, no doubt in that. But it is this a kind of okay, it requires some kind of computational. Okay, we are having a non-linear curves. Okay, nowadays not a difficulty. We can establish okay these non-linear curves. Okay, the boundaries okay between okay two mechanisms can be a linear. Okay, can be a linear or can also be a we also see non-linear paths. So I think this was started in 1972. Okay, afterwards, okay, I think many scientists started working how to make it a simpler way of okay representing deformation mechanism. So there, I think the one scientist and his group, okay, Langdon and his group, okay, came up with a slightly different way of representing mechanism map. Here, y-axis still sigma by g, and grain size has been maintained constant. Here, instead of T by Tm, they have taken inverse of okay homologous temperature, inverse of homologous temperature, Tm by T. Okay, that means this is a melting point. This is a high temperature one, and this is a low temperature one. 2.5 means actually 0.4 times of melting point. Okay, so typical. Okay, so this is a creep domain. Okay, 0.4 to okay 1 homologous temperature. Okay, this is the x-axis. So they came up with this, for example, this boundary from dislocation creep to cobble. Okay, it was like a non-linear thing. Here, look at here, climb to cobble became a linear thing. Became a linear. Okay. All of them are linear. Then we can know boundaries very easily. Okay, and come to know what type of okay mechanism is taking place. So this is a simpler simplifying the okay Ashby map. Okay, so it's one way of okay, varying sigma by g versus a Tm by T. So how do you establish these boundaries? For example, I want to know okay the boundary between climb and cobble and Nabar herring or Nabar herring to climb. How do you okay establish? Okay, how do you establish? What should you do if I want to know the boundary? Okay, where the strain rate is a okay constant for both of them. Am I right? The boundary basically indicates that the strain rate, the creep rate, if you take a creep rate, is a constant, okay, is equal for both the mechanisms at the boundary. That's what it's called boundary. Okay. So typically, you have to take okay equate those equations. For example, here, if I take, I want to know between cobble creep and Nabara herring, where that boundary starting. What should I do? I take the equations, their respect to constitute equations, and equate them. Okay, because where the strain rate is constant, same okay for both of them. So under that gives you boundary. So by just rearranging terms, okay, rearranging the terms, I can get Tm by T. Okay, Tm by T because my x-axis is a T. Okay, here. Okay, look at here. So I do get okay because there's no stress. Stress became okay cancelled both of them because both of n is equal to 1 for both the mechanisms n is equal to 1, so get cancelled out. Now what I'm seeing the temperature is now okay. Look at here between the Navarro herring and cobble. Okay, it's independent of stress. Independent of stress only we have a boundary. Okay, for the constant okay Tm by T. So one can actually by plugging okay values of okay Navarro herring constant, cobble constant, okay, and diffusive coefficients and grain size, okay, and melting point of okay material. So and taking the lattice diffusion grain boundary because respect okay. So we can get a the boundary at which okay we are seeing between the Navarro herring to cobble transition. Okay, so like that what you have to do, take the, for example, if you want to know the boundary between these two, I have to take these equations. Okay, take these equations and establish the okay relationship how it's coming. Okay, similarly between climb and Navarro herring, look at here, for example, cobble creep to high temperature climb, you take the respective equations here. Okay, stress only okay still there because we are talking high temperature. For example, assume that the high temperature climb is happening, we take sigma by g to the power of 5. So if you can okay, if you look at rearrange them, I do get okay sigma by g is going to be like a okay y is equal to okay mx plus c. You'll get a y equal to okay this is a okay x is a tm by t, this is a okay m slope, and this is a c, y is equal to mx plus c. So that's why we are getting a linear okay line, the slope. Okay, we're having a slope of QL minus QGB by 4 into 0.3 times of RTM. Okay. Okay. Similarly, Navarro herring to high temperature climb. Okay. Okay. We do rearrange them, we'll get a dependence of okay. This temperature term is okay, gets cancelled because both of them are lattice diffusions. Both of them are lattice diffusions, that's why it gets cancelled out. So there's no temperature. That's why you're getting a okay constant sigma by G. So where these three curves intersect, that basically gives a common. Okay. This is how actually people construct a simpler way of deformation mechanism. Is it clear? Any doubts? Yeah. Hello?
Yes, sir.
Hello? Yes,
Yes, sir.
yes, sir. So is it clear how to construct a deformation mechanism map?
Yes, sir.
So without okay using any computational thing, just plugging the values and construct the okay boundaries between the various okay different mechanism maps, different mechanisms what we see. Okay.
Sir, on y-axis we have written sigma by g. Basically, this sigma is a shear stress only, right?
No. Sigma is the stress, true stress.
True.
G is the shear modulus.
Okay.
True stress, true stress. It's a true stress. Okay, we are talking about polycrystalline materials here. Okay, so okay, is it clear?
Yes, sir.
Okay, so if we have a coarser and coarser grain size, we are basically going towards okay, we are going coarser grain size. There's no boundaries. Okay, so boundaries, the volume of boundaries are going to come down. So diffusional activity is going to come down. Okay? So the diffusion is less, so we don't see diffusional creep kind of things will not be seen. Mostly dislocation creep kind of activities are going to happen. Dislocation creep mechanism is going to take place. That's why actually if I have a between between polycrystalline and single crystal, polycrystalline material have a lot of boundaries where the diffusion plays significant role. That can lead to reduced creep resistance. If there are no boundaries, so single crystal, we do mostly see a dislocation creep. The dislocation creep strain rates are high, typical. So this is how actually people design the things. Okay, this is one way of graphical representation. So if I take, for example, if I want to know between grain size and stress, grain size and stress, maintaining a constant temperature, T is equal to 0.9 times of melting point. Okay, so look at here. Okay, this grain size is normalized with the Burgers vector. Stress is normalized with a shear modulus. So look at here. So we do see this kind of at higher stresses, we know that dislocation creep is the dominant mechanism. At low stresses, we do see diffusion creep mechanism going to come into picture. So again, look at here at very coarse grains, we do see Harper Dawn creep. Okay, and we do see Navarro herring creep is coming below this Harper Dawn creep, and below we're going to see a cobalt creep. What does it mean? If the grain size is finer and finer, cobalt creep is the dominant mechanism. Cobalt creep is the dominant mechanism. If you take very fine grain nanocrystalline materials, we can see cobalt creep can take place very easily because the grain size dependence is basically d to the power of -3. Okay, finer the grain size. Okay, finer the grain size, we are going to see higher the creep rate. Sigma epsilon dot is in proportional to sigma to the power of -p. Okay. If the P equal to 3, that means actually finer the grain size, higher the strain rate. If P is equal to 0, that means grain size dependence is not there. Okay. That means if it's a coarse grain, single crystal, there's no grain size dependence. Okay. So that way your creep rate is going to come down. Okay. So this is one way of representing T by B versus sigma by G. This also basically you have to take and equate the terms such a way that we should have y is equal to some mx plus c kind of format. Okay, x is a sigma by G. So if we take the equations, equate them and make sure that you arrive a relationship between d by b versus sigma by G at a constant temperature, you will get this kind of boundaries. Okay. So another way actually d by b versus Tm by Tm, d by b versus Tm by T, maintain a constant stress, we'll have this kind of boundaries. Okay, these are very different ways of representing the domains of different mechanisms which can take place as a function of some variables, Okay, so I think already I think showed for the previous one. Okay, sigma by G versus Tm by T. Okay, I will give a one assignment on constructing d by b versus sigma by G. Okay, for given some material, I'll decide some temperature. At that temperature, you may have to identify these domains. Okay, so I think I'll stop it here. I think we are almost close to 12:25 now. Okay, so if there are any doubts, please let me know. Any doubts? Is it clear? Whatever I think we have discussed so far for the creep deformation. Is it fine? I think yeah. So I don't know what happened. Am I online?
Yes, sir. Yes,
Yes.
sir.
Okay. What happened? Suddenly everybody got silent. So I'll stop it here because okay. So if there are any doubts, okay, you can they can stay back. Others can leave the today's lecture. I'll stop recording. Okay.